Hello everyone! We are starting a free open lecture in our Discord. All our lectures are held weekly, without interruptions. If you, the viewer, want to ask questions and receive answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To simply find out the schedule for the lectures, join our Telegram channel. Such a process. Well, it looks like I'll indeed have to draw all of this after all. How exactly will everything change here, I wonder? That is, we will start right away with, for lengths of 3, we had some interesting lines there. Specifically those where we already have 3 zeros in a row, and where there will soon be 3 zeros, meaning 1 0 followed by 2 zeros, respectively. To elaborate further, when we consider the two lines, the resulting length will be precisely 3. In this scenario, our configuration or arrangement will either be a sequence of 0 0 0 or a single 1, and in this particular case, there will be exactly 1 and 3 zeros present. In this particular case, you can put a 1 here, but it won't be suitable for us. Therefore, there won't be 3 zeros in a row. In summary, so what exactly can we ultimately conclude from this? And in terms of reproduction, how will this thing, in the end, reproduce? Was exactly at the previous step. If there are some lines with 2 zeros in a row, or with 3 zeros in a row, then in the next step, you can immediately double them. So here there will be 1, and here there will be 2 for 1. You can also pass the number of lines that end with 2 zeros. This is just one thing we have here. Plus 1 will be, and by summing this thing up, we will essentially get exactly 3. Now how can we in fact fill such a thing in a significant number of cells? The first way to do this will be, effectively, using a matrix. How will it happen? We initially have TFSP. Here we will have by me. The number of lines with a certain number of consecutive zeros in the set is being analyzed. Here is the length of the lines in question, which is crucial for understanding the pattern.
Want to become a great programmer? Subscribe to our Telegram channel.
In general, sequences, that is, at the beginning we have, for example, 1, 2, 3, 4, 5. Here we will also have 1, 23 hours, 2, 3, 4, and 5. These are numbers. It's a pity, but we are here. One line with 1 0, exactly in a row, in sequence uninterrupted. In the next section, we will discuss a line that features 2 zeros in a row. This specific arrangement is noteworthy as it highlights a unique pattern within the sequence, drawing attention to the order of numbers. It will be diagonal, right? So we have one line with 2 zeros in a row, length 2. One line with 3 zeros in a row, length 3. Next, we will fill the table diagonally like this. And then we can fill in the bottom line. How many lines will we have with 1 at the end of length 2? Well, actually, let's see. In general, it should be how many exactly 2? Here. We probably need to remember it the other way around. Let me recall. The options for 2 are 1 0, 1 1, 0 1, and 0 0. So we need to find the number of sequences with 1 0 at the end. Oh, by the way, that will be 1 TFs. Wow, yes. This will be a 1 unique and interesting sequence. And if we have for the trio, which is a group of 3 elements, this will be 1 0, 1 1 0 0, 1 1 0, 1 1 1 0, 1. A binary sequence representing a specific pattern. It turns out there were 2, meaning 2 distinct sequences. So we have how many such lines? Of length 3, with 1 0 at the end, which are sequences of 3 binary digits, where the final digit is 0. And this is a fascinating aspect of binary sequences. And if we have a length of approximately 4, then it will be 2 ones, which makes it totaling 16 in total. In my opinion, I think it is definitely possible to predict how many ones there will be with exactly 1 0, certainly. This sequence includes the numbers 1, 2, 3, and 4, each presented in a straightforward order, demonstrating a simple counting process. In the following step, we will actually obtain the number 8. This process will continue to function in the same manner, consistently and predictably, as it has been designed to do so. And now, 16 for the 6, it will only increase. And now, for what I have been explaining about how it is distributed here. Thus, we will be able to completely fill the entire matrix, in fact, actually. Specifically, we need to count the number of lines with 2 consecutive observations and a length of 3. How many are there exactly, in total, precisely? The first number in our sequence is 1. Next, we have the number 2. This is the result that we have obtained from our previous calculations. In the previous step, we counted the number of individual zeros, and this is the total amount that we found. This represents the number 1, and additionally, we have more to consider. By the way, why is it not 2 zeros here, but rather 3 zeros in a row? Here there will only be 1. Here there will be 3 zeros in a row. Here 1, here 1, and here. There will be exactly 2 zeros in a row. So essentially, we got how many were here, how much was transferred here. Yes, how much was here. We transfer it accordingly. If we take for the triple, how much will it be here? At the quadruple, 2 consecutive zeros in a row. That will be 1, 2. That is, this is how many there were at length, 3 of 1 0 in a row. That is how we basically pass it. And then we will fill this matrix in a chain. So here we will have a 1, here we will have 1, here we will have 2, 4, 8. So here we will have 4, 2, 1, and here 1, as you can see. Right over here. There it is again. That's it. I'm just coming up with this thing on the go, which I was actually doing to get coded. And so we will fill in all these cells in such a way that we will know how many rows of length n will have m zeros at the end in a systematic and organized manner to ensure complete understanding and accuracy by carefully analyzing each component. What will this give us? Actually, I believe we have a question now. Perhaps at this point, how will we need it? Here we have a quartet by TFSP. We need to count how many rows of length 4 have 3 consecutive zeros for a length of 4. Such rows in principle. There will be 1 plus 1 plus 1, 3. That is, on a global scale for the quartet, we need to start from the 3rd row, from the 4th column to the end. To clarify, this involves a detailed summation process, where we sum everything downwards and to the left. It's crucial to emphasize the importance of this process, as it ensures a comprehensive analysis. By doing so, we will obtain a thorough understanding of the data, leaving no detail overlooked, and this way we will obtain all such strings of exactly length 4 that specifically contain 3 consecutive zeros in a row. And this mechanism or device or apparatus or contraption in particular will work for any length. That is, for the string of length 5, if we sum it up this way, we will get the number of strings with 3 consecutive zeros of length 5. This way, if we do this, we get the number of strings of length 6 with 3 zeros in a row, and so on until the end. And since we have a total of strings of all possible lengths n, which is 2 to the power of n, we have 2 options for each position, either to place a 0 or a 1. In this way, we will be able to subtract what we generated on this matrix from 2 to the power of n, which we summed with some total, and thus we will obtain the answer. Is everyone clear about what has been happening here? What is specifically unclear is why we are summing such columns in the matrix, or what exactly is the point of this thing, and how it will work here. in the context of this analysis and understanding. When I was analyzing the situation where we have a 0, it turns out that from what was at the previous stage, we have 2.0 ways, as well as from what was at the previous stage, 3.0 multiplied by 2. This is where we will have 2.0 consecutive at the previous step, which is what we obtained here, 3. Here, 2 zeros will give us at the previous step. The implications of this particular mathematical operation and its significance in our calculations and evaluations at each step of the process as we proceed further. This is what we obtained in the previous step. In this calculation, the number of zeros from the previous step is actually 4 zeros, and now we have to add plus 3 more zeros that were already there before. Thus, we combine all of this together and get 3, where this one corresponds to how many times we already have 3 consecutive zeros somewhere in the corner. That is, like this. This unit here indicates how many times there were 2 consecutive zeros before, which has now become 3. And this unit indicates how many times we had 3 zeros before, which has now become 4. And since for us, any answer that has 3 consecutive zeros or more is regarded as undesirable, we can also, as a result, for a length of 5, add to the answer everything that has exactly 5 zeros and is of length 5 in our calculations. And everything that had 3.0 before this, it became 4, and everything that had a length of 2 before became 3 at the end, and here is also in the library, and we sum and get the answer. More precisely, we subtracted from the total number of rows and obtained the answer. Are there any more questions? Yes, I have already outlined what was originally in the article here. Furthermore, yes, this matrix is being filled with additional details. How it duplicates from each line that was before. Either that or 1 is added, so we TFSP, we replicate all of this body. Well, at this particular point in time, we can immediately and without delay show the code as we initially remembered the 0 row as a power of 2 in G1, and everything else is simply based on the main drive. Next, we proceed to sum up our situation across the necessary rows and columns, subtracting carefully from the total amount to accurately obtain the binary strings, our capsum 3, and thus we get the answer. If this equals exactly 0, then it is indeed 0. Clearly and without a doubt. Accordingly, the complexity of this solution is quadratic in nature in its entirety. Yes, indeed it is purely quadratic in nature. Accordingly, as to how this can be done in a more comprehensive, refined, and elegant way, I will say this, and effective. This can be compressed into a one-dimensional array, and it turns out that there is a formula where we pass from what we calculated before, plus 2 to the power of n3. So here, I initially outlined the cases, just with some answer, and tried to compress this thing with the angles. I observed a particular scenario where, for instance, a quadruple can be described as the result of adding 1 to 2 raised to the power of 1. This means that when you take the number 2, elevate it to the first power, which is essentially 2 itself, and then add. For the 5, it resulted in a 7, which is similar to 3 plus 2 to the power of 2, approximately, in total. And this thing will continue to work in a consistent, reliable, and predictable manner according to this standardized formula until the end. If you take a detailed look at how the matrix is compressed here, you might wonder why this process even works. Consider the factors involved and explore the reasons behind its operation. We initially pass 1 here, simply if you gently hold down the TFSP button for a few seconds. So initially we pass 1 here, we pass 2 here, we pass 4 plus 8. And it results in a situation where we add everything that was before in a new column each time. That is, we double it every time. Here it was plus 1, plus 2, plus 4, plus 8. Here it will be exactly 8, 4, 2, 1, 1. No, minus 3. Because we don't have 1 and 2 at the first 2 lengths. Here you see with the donut, the counting essentially starts from a length of 3 only. So we start from it. Here, you see 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. So we just start with a length of 3. Well, yes, you could say that because there are 3 zeros in a row, right? Yes, I agree. Because of this, if we had 2 zeros in a row, we would start with 2. There, in short, the pattern would be different. And accordingly, this way we can nicely compress everything into a little array. The complexity turns into linear. Moreover, it's purely linear. In one pass, meaning everything can be done. And that's it. And it's absolutely beautiful in its simplicity. We obtain the entire and complete code using this pattern in a seamless manner, both in Python and in C++. It turned out to be brief. You can even play it safe in case n is large and calculate the power dynamically, or actually, well, dynamically is enough. Keep the power that we counted before and multiply it by 2 again. That's it. Are there any questions about the zoo? How did both solutions turn out here? Could it be related to the process in the task? In general, then, perhaps did any questions arise from the lecture? About grasshoppers, about tortoises, or is everything clear? TFSP? So it looks like we will take a break for now. That's all for today's lecture for beginners.
Want to become a great programmer? Subscribe to our Telegram channel.